All right, hello class, and welcome back to lecture 14. Make sure our tablet's working. All right, so this is our third and, well, it's not the last we're going to see of robust control, but it's the last lecture devoted perhaps exclusively to robust control, I suppose I could say. The lectures on SOS, which follow this, also deal with the problem of robust control, but also deal with nonlinear stuff. And so it's sort of a mixed bag from lecture 15 on. So in this lecture, we are going to have we're going to introduce quite a few LMIs for robust control. A fraction, of course, of the LMIs that are out there. So you can just look at Boyd's book on LMIs and systems and controls, and you'll find many more. But I think what we're going to cover today, and what we covered in lecture 13, of course, was also a highlight. What we cover today are the highlights of LMIs for robust control, in the LFT framework. All right, so we're going to be focusing on that LFT framework. And as I said, we'll mention this a bit going forward, but the LFT framework allows us to understand or to analyze systems where the uncertainties don't enter quite as neatly as they do in the additive, the separable, polytopic, and interval uncertainty case, which we considered in lecture 13. So I think you're going to have two parts. So the first part is going to consider the problem of unstructured uncertainty. In the LFT framework. And then starting with lecture, I believe, slide 17 or something like that, we'll consider the case of structured uncertainty. Now, as you may remember from lecture 12, when we introduced the whole robust control framework, structured uncertainty is actually quite common, especially when you have uncertain parameters that you're trying to analyze in the LFT framework. And so these are probably more accurate models of uncertainty than the unstructured case, which is, I think, less common. But of course, if the result holds for unstructured uncertainty, it certainly will hold for structured uncertainty. So we'll try and deal with those separately. Right? We'll have a nice result in the unstructured case with the S-procedure, which is similar to one of those tools that we've used so far, including the Schur complement and the KYP lemma. It's one of those sort of LMI tools which gets a lot of traction. Right? So we'll see that as we get to lecture. I think it's slide 10 or something like that. Okay. So overview of where we are. So in lecture 13 we covered these two cases. The case where we had these additive representations of uncertainty, and the uncertain parameters were either polytopic or interval. So we covered that case in lecture 13. In this case, in this set of slides, we're going to be considering the remaining cases. So in this, here we have the structured part. That's we're going to cover that in part 2, part B, I guess, of this lecture. And the unstructured case. So there's two cases where we have static uncertainty. That's where, if we consider our nominal system and our uncertain system in the LFT framework. The static case is where the Q of t is a function of P of t, where, right, at every instant in time, we can guarantee, for example, if delta is less than 1, we can guarantee that Q of t, right, the norm of Q of t is less than the norm of P of t, right? So we know information about the relationship between these signals at every moment in time for all t greater than or equal to 0. By contrast, in the dynamic uncertainty case. There's some relationship between these two, but it's not a temporal relationship. So it's a signal-based relationship. So here we treat the uncertainty as a matrix. And here we're treating the uncertainty as a system. So in this case, we would have, say, for example, that the norm of Q in the L2, right, the signal norm of Q, say, for example, is than the signal norm of P. Now, most of the results that we're focusing on, of course, are going to be on this this static case, right, where we treat delta as a matrix, as a parameter. We will cover a little bit on the dynamic case. As we'll see, however, there's not too much exciting you can say about the dynamic case. And in fact, in the dynamic case, really the small gain condition turns out to be as good as you can get in that dynamic case. But so we'll cover that briefly, right? So that's part A of this lecture. We're going to cover those stuff. So just to rehash, right? Here we are. Here's our LFT. Right. We can add another input and output if we want, right? For exogenous input, W and Z, if we like. In the previous lecture, lecture 13, right, we considered the case where the system matrices, right? This is a system matrices. The uncertainty adds or enters into the system matrices in an additive separable manner, right? So that we can separate each of the parameters of the uncertainty. They don't multiply each other, they don't divide each other, and then they just add, those parts add together. So that's a very special case, and of course, if you don't have that special case, which is in most cases, I would suppose, then we have to use the LFT, linear fractional transformation. Right. And so what we learned, right, was that almost any form of rational uncertainty, parametric uncertainty in particular, can be represented using the LFT. So the system matrices, these are the system matrices in this case, are represented as an LFT. These aren't systems, these are matrices. So these are this is the A, B, C, D matrix, right, which relates x dot equals x, and then the exogenous inputs there. I guess we have F here. I guess we should make that F to be clearer. Although actually in our case we should say we're focusing on the case where the output here is, at least to start, we're focusing on where the output there is P and the input here is Q, right? So let's not get too hung up on this because we'll make these all very explicit. But in that case, actually, we relabel these things. I think we use M, Q, and N for those matrices. I don't know if those are the best choices of letters. They seem kind of arbitrary, but they're sort of related. M, N, P, Q, M, N, O, P, Q. So they're sort of related, but you just have to remember that, right? That's we'll go through that representation several times. Okay. So in this first part of the lecture, right, part A, we're going to concentrate on the tool for analysis being the S procedure, in part A, and that'll allow us to handle static, unstructured uncertainty. And then in the second part of the lecture, we'll focus on the structured singular value as a somewhat different tool, which allows us to account for the structure of that uncertain block. So we just don't treat it as a big matrix. We know a little bit more about it, so we can say a little bit more. Right. So okay, but right now we're working on part A. Right. So okay, let's go through robust and quadratic stability again. So if you recall, robust stability ensures that for any given value of delta, so for a fixed delta, the interconnection is stable for all fixed delta, right? So this is In particular, you could say that the A matrix is Hurwitz. We could also do a system sort of level representation. We can say that the operator I minus delta M11 is invertible. So if we use the four system representation of M here. So that's robust stability. As we said, however, if delta is time varying, robust stability doesn't prove stability, but if the delta is fixed in time, it does, right? So robust stability implies stability if delta is not time varying. So let's go now to the system matrix representation. So to start, this is what we had on the previous slide, the robust stability in terms of the four system representation. Right. So now let's go and redefine these things for the system matrix representation. Right. So this is the matrix representation. Really here we only have four matrices here, and really I think this should be P and this should be Q, since remember we're doing the LFT for delta, which P comes out there and Q comes down here, delta M. Right, so we've got this linear fractional upper star product for the system representation. So now let's define robust stability now in terms of that system representation, so the star product on the system matrices. So these are the closed loop system matrices. I guess I should make this plural here. So basically the definition of robust stability, and now we've added these other matrices, closed loop, for, in this case, the LFT, right? We're redefining all these things for the LFT, because in the previous lecture 13, we defined them for the additive case, and now we're considering the LFT. So I mean, it's not complicated, right? The concepts are the same. Basically, we're defining robust stability in terms of the properties of the eigenvalues of this closed loop system matrix. So basically, so actually I should these should actually be, because we're doing the upper star product, actually I should these should be 1 2 2 1 2 2. So I should swap all of those things because we're actually doing the upper star product, right? So apologize for that. 1 1 1 2 2 2 2 1. Right. So basically, if the closed loop A matrix is Hurwitz, has all negative eigenvalues for every delta in delta, then we define that as being robust stability. And we add a little term here, beta. So for some, it can be arbitrarily small, but for some beta, we would like all of our eigenvalues to be to the left. This is the complex plane. So we want all the eigenvalues to be to the left of some beta, right? So this can be very small beta. And the reason is that what we don't want is, because remember, this is a condition that holds for all delta in a set. And that means it has to hold for an infinite number of matrices. And so what we're trying to avoid here with the beta is the case where, right, there's like certain deltas, whereas you get close to the limit of the set delta, which sort of approach the imaginary axis. And believe it or not, that actually happens sometimes. So if they converge to the imaginary axis, we're not going to consider that robust stability. And so that's why we add the extra little beta I thing to add something to our eigenvalues. It's kind of a technicality, and you don't have to worry about it too much, because we're not going to use robust stability too much to begin with. So there's that. But we do have to be careful when we're talking about sets or constraints, especially on eigenvalues, which have to hold at an infinite number of points, because they could sort of approach badness but not actually be bad for any delta, and that tends to be what we call bad anyway. Right, so if you have, here's your uncertainty set of eigenvalues, and here's the imaginary axis, right? It may get up to that point right there on the imaginary axis, but not actually reach it. Anyway, I don't want to get too deep into that, right? But that's why it's there. Similarly, for discrete time, we define robust stability in terms of sureness. Specifically, if you're not familiar with this little symbol here, this is the spectral radius, which is the maximum value of the eigenvalues of A. So the maximum of lambda such that lambda is an eigenvalue of A. Right. So the spectral radius is just the magnitude of the largest eigenvalue. Right. So for sureness, we want that largest eigenvalue to be strictly less than 1. And again, because we're constraining these eigenvalues over an infinite set, right? There's an infinite number of points in this uncertainty set. There's an infinite number of matrices the delta can possibly take. We add a little bit of strictness, right? So we want some beta greater than, we should add, there exists a beta greater than 0. Some strict, it could be arbitrarily small, 0.000001 or something like that, but we do want to make it strictly negative. That's just the definition. So robust stability and in continuous time, and robust stability in discrete time. As we talked about in lecture 13, however, robust stability is not a terribly helpful concept because it only works in the case where your uncertainty is not time varying, and we typically like to have results for the case where it is time varying, so not as helpful as we would like. Like robust stability, of course, we can also extend quadratic stability to the LFT framework, right? So in this case, again, if we focus on this upper star product, right? So here's our LFT, M delta. And here we're not going to include exogenous inputs for the moment. So if this is our system representation, so this is our system matrix, closed loop system matrix, then quadratic stability has the obvious definition. So we just replace A in lecture 13 with the upper star product here, right? And we get a condition on the eigenvalues of this closed loop system representation. Right? So in the case, right, where there's like exogenous inputs, we're just to have the 1-1 block of this closed loop system matrix. So this would, if we had exogenous inputs W and Z, right, then this would be 4 by 4. In this case, we're just going to ignore those and make this a single matrix. Likewise, this is easily extended to the discrete time case as well, right? Where again we just focus on the 1-1 block, right, of that discrete time state update matrix. So, like as we discussed in lecture 13, right, the quadratic stability condition is not defined on the representation, not a function of the representation. It's actually an LMI per se, or a Lyapunov condition per se, if you can think of it, if you want to think of it that way. It's an LMI condition or a Lyapunov condition, which are almost synonymous. So we bypass the representation entirely and we go straight from an LMI condition to the properties of the system. And remember, of course, quadratic stability is in general conservative, right? There we had a counterexample in the previous lecture where the system was stable, but it was not quadratically stable for time-varying uncertainties. Likewise, so this says there exists a single quadratic Lyapunov function, which doesn't depend on delta, right? So doesn't depend on delta. So Lyapunov function doesn't depend on delta, right? So a single Lyapunov function which works for every possible value of that uncertainty, right? So this holds for all delta in delta. Again, this is an infinite dimensional LMI, so really I should say infinite D LMI. So it's an LMI condition which has to hold over a whole set of possible uncertain matrices. Right. And likewise, for discrete time, it's similar. It's the Lyapunov function, right? V equals x transpose px is a Lyapunov function which is decreasing at every time step for every possible value of the uncertainty. So it's, again, no dependence on delta, right? It's a single Lyapunov function which works for every delta in that uncertain set. So again, right, this proves sureness, right, for every fixed delta, but it actually proves more. It proves that the system is stable even with time-varying delay. So these both imply stability with not delay, uncertainty, with time-varying uncertainty. Right. Okay. So now we're gonna be looking for conditions which enforce these quadratic stability conditions. So we'll be focusing in this lecture not on robust stability, but almost entirely on enforcing these notions of quadratic stability. The difficulty being, of course, enforcing them, right, for all delta in some uncertainty set. So how does one enforce those kind of constraints? Of course, in the polytopic case, right, we had this nice result which says that if in the polytopic case, remember what polytopes look like? They're sort of the weighted average of a set of vertices. So that's a polytopic case. Now we're going to be considering norm-bounded uncertainties. So actually our uncertainties, so our deltas were there. Now our deltas are in a ball, and obviously I guess you could say that if it holds on the circumference of the ball, right, then it holds, but that's not very helpful. So we showed how to enforce these conditions in lecture 13, these two conditions in lecture 13 for polytopic uncertainty, and now we're going to be considering norm-bounded uncertainty, so that the norm of delta is less than or equal to 1, something like that. All right, so yeah, there we go. Stage is set. We have parametric uncertainty, which means that this is a matrix. Q of t equals delta P of t. Delta is norm-bounded, right? So norm-bounded. So this matrix has size less than 1, which means its maximum singular value, by the way, is less than 1. And then parametric, which means that this equality holds, or this equality holds here. Okay. And okay, so let's what else is there to say here except that maybe we're giving some names to these four matrices in M. This is a bit confusing, of course, because this M is not this M. Right? Those are not the same M, so sorry about the overuse of M here. Probably P would have been a better letter. Let's call it P. Right. Of course, then we have a little lowercase there. Anyway, so but this this M has a system for matrix representation A, M, N, Q. Right. So we want to enforce the stability of this system, right? For all delta in the norm-bounded uncertainty set, where the size of the matrix, and here we mean the maximum singular value of the matrix, is less than or equal to 1. So again, right, we're again looking at the LFT of that four-system matrix, four matrix representation with the uncertainty set delta. We could solve for that, right? So we could solve for that by constructing that LFT, right? That's the star product there. We're not going to actually take that approach because it doesn't get us very far. We'll see later on that you can do something with that, but we're not gonna focus on that approach. We're going to actually pose the question in a slightly different way. So we're going to consider quadratic stability, right? So we're going to be looking for a single Lyapunov function, single quadratic Lyapunov function. So this is quadratic stability. Quadratic stability means there exists a single quadratic Lyapunov function which works for all values of delta, right? And so we want to make sure that this Lyapunov function is decreasing, b dot less than or equal to 0. Actually, we want it to be strictly less than 0 because we're strict. We want it to hold for over a set, and we want that to be 0. And so what do? Well, we take this this quadratic Lyapunov function. We plug in t here, of course. We take its derivative. Then we get some x dots here. X dot is, of course, given by this equation here, so we just plug that in to x dot. And we get, right, ax plus mq, right? So there we go. So here's the derivative of the Lyapunov function, and that's what we want to make negative, right? Of course, we want it to be negative for all x, but we don't want it to be negative for all q because that doesn't make sense, because q is not just anything, right? It's related to p. If it was just anything, obviously this would never hold, right? You could always find a q that would make this thing positive. So it can't just hold for all q, right? It has to hold for all q, where q, the norm of q, well, q of t equals delta of t, p of t, where p of t, of course, is given by p of t is given by equal to n x, this thing here, p of t, and x of t plus q of t. All right. And delta is less than 1. Maximum singular value less than 1. So we put those two together, right? We plug these two, this thing, right, plus this thing, and we get then that we need this Lyapunov function to hold for all q's which are smaller than nx plus qq, because remember this is p of t, right? This is q of t. Right, so the norm of q is less than or equal to the norm of p, right? Because, right, delta is less than 1 and q equals delta p. Right? So we want this this LMI condition. Well, not quite an LMI condition quite yet, but we'll phrase it as an LMI condition. We want it to hold for all. Actually, I should think that's a mistake there. All q and x, such that q is less than the size of nx plus qq. So what are we going to do? The problem is we have two. First of all, we have something which is not quite an LMI yet because it's got p and q, x and q in it, and it only has to hold over a subset of q. So the q's which satisfy this inequality here. So we're going to try and write this out as an LMI. So we're going to do that by right? Writing out Q and X separately, right? So we're going to stack them together like that. And so first of all, we'll show we show that this actually is an LMI, sort of, right? And we do that by expanding out these terms. So obviously the norm of Q is just this term here, right? Because 0, 0, 0, this is just Q transpose Q, right? So that's just Q transpose Q, which is equal to the norm squared. And on the other side right here, we just have the norm of nx plus qq, right? So nx plus qq, right? So this is nx plus qq. And transpose with itself, right? So this is just the norm of nx plus qq squared. So here we've got something that looks sort of LMI-ish, right? Here, and here we also have something which looks LMI-ish. Let's multiply out these two terms, and we get this this matrix here. So we want this condition to hold for all xq, right? Such that, and here we can just move this this term here to the other side, such that xq transpose negative n transpose n, negative n transpose q, negative q transpose n, negative q transpose q, plus I, xq is less than or equal to 0. Right. So we want this. We have sort of an LMI, which we're also going to put in sort of a similar expression, to hold for all x and q, such that this other LMI-ish like thing holds, an LMI condition. Right. So again, it's we're enforcing an LMI over a subset, right? A set of x and q which satisfy this constraint. So if we formulate this specifically, we would now put the derivative condition. Let's take that derivative condition we had here, put it also in an LMI format, and we want it to hold for all x and q such that that inequality on the previous slide. So we'll take those terms, and as we said on the previous slide, we formulated as that condition. So basically, what we want is and this inequality to hold for all x and q, right? Not for all x and q, right? Not just every x and q. Otherwise, it would just be an LMI and we'd be done. But it would never be satisfied because this is 0. So if you have a matrix with a 0 on the diagonal, that can't be less than 0, and it also can't be positive, greater than 0. Right? So obviously, this will never hold, right? Just for all x and q. So we have to say it holds for all x and q such that x and q satisfies this other inequality over here. Right. So again, right, using the logic, and I think I go through it on the next slide, this system, right, where q is related to p through delta, and delta has that norm less than 1, norm bounded uncertainty. Then that system is quadratically stable if and only if there exists a p greater than 0, such, and that's a quadratic Lyapunov function. Such that Lyapunov function v dot is decreasing on those x and q's such that this inequality is satisfied. So this norm bound on the norm of delta, and again, this is a matrix. Delta is a matrix, so it has to hold for all time. Right. So it's quadratically stable if this is satisfied for all x and q such as this. So this is a weaker condition, right? It only has than an LMI on here. It only has to hold for a subset of these states, so a state-dependent LMI. And those are actually rather hard to solve. But before I get into that, I'll talk about just go through that proof again briefly. Again, and here there's an interesting point, right? That constraint right here, right? That's an ellipsoidal constraint. On x and q, right? So it's we want the LMI to hold on an ellipsoid, basically. So generally, enforcing LMIs on a subset is hard. In fact, copositivity is a particular case of one, which is NP hard. But we'll see that this one's not so hard. The proof of this, again, is just combining those the logic on the previous slides. It's relatively simple. If this LMI is satisfied for all x and q such that this LMI is satisfied, then if we let v equals x transpose px, then v dot is equal to this. And this, we know that q is less than nx plus qq. So we have that this, this LMI is satisfied for all q's and x's which satisfy the system. Right? Since if q is delta p, we have that q is less than p, and of course p is nx plus qq. So sufficiency argument is relatively straightforward. The only if direction, the necessity is also relatively straightforward, because we have these are all equalities, right? We haven't done these are all if and only if statements, so we haven't done anything conservative at this point. Of course, quadratic stability is itself conservative, right? But the condition for quadratic stability we proposed is not. Right? Right. Now, of course, the problem, right, is that this is a hard thing to prove, right? That the if you basically what you're trying to do is show that you have a quadratic form and you want it to be positive for all x on a subset, right? You want x transpose fx to be greater than or equal to 0 for all x such that x transpose px is, I believe, we had less than or equal to 0, right? So that's the form of the problem we're solving. So we need to be able to enforce constraints like this. Now, generally, as I said, this is an NP hard problem. If you actually made it what seems like a little bit easier, if you wanted x transpose fx to be greater than or equal to 0 for all x such that x is positive, right? And this often comes up, say, in systems where the state variables are necessarily positive, like in biological systems. Sorry, actually, that's the wrong orthant, right? Right, so in biological systems, in many physical systems, the state variables are always positive. Cell counts can't be negative, for example. And so you want to find a Lyapunov function which is decreasing just on the case where the cell counts are positive, for example. You would think that that would actually be easier than the one we're trying to enforce, which is quadratic. This is linear. This is about as linear as you can get. But it turns out that this one is actually, has a name. It's matrix copositivity, and people have studied it for a very long time. Very well-established topic. But it's still unsolved, right? It's solved in the sense that we know it's at least NP hard, right? So that problem is actually NP hard. So it seems like we're trying to solve a harder problem than an NP hard problem. But actually, it turns out that it's not the case. Our problem is actually a little bit easier than the NP hard problem. So fortunately, right, that's good. And the big tool, right, that we're going to introduce on this slide is a solution, right, to this problem of enforcing an LMI on a subset. And that's the S-procedure. It's extremely well known, extremely useful condition, which enforces an LMI on what's essentially an ellipsoid, right? So what does the S-procedure do, right? So it's really a theorem, or but we call it a procedure. I don't know. The theorem itself doesn't actually have a name. Actually, I'm labeling it as a corollary, but so we just call it the S-procedure, right? And it says that it's a very interesting result. It says that this well, here I was calling it Z. Z transpose Fz is greater than or equal to 0 for all Z in this quadratic set, such that Z transpose GZ is greater than or equal to 0. And here it says if, but it's almost only if. Okay, but I'll just do the if for now. If there exists a scalar, and that's particularly interesting, a scalar value tau such that f minus tau g is greater than or equal to 0, right? So this is an LMI if g is not a variable, right? So it's introducing a new variable. So you have to find this. We don't know what this is in particular. You can't use bisection or anything like that. It's a new variable you have to search over. Right? You can have variables in your f. But you can't have variables in g because then the new variable would multiply the g and create a bilinear term. Right? So no variables in here. Because otherwise you'd have a bilinear term. Anyway, but assuming that there are no variables in G, this gives you an LMI, which is sufficient at this point for positivity of F on this quadratic subset. And the proof is actually relatively easy, right? Right, let's suppose that Z transpose F Z is greater than or equal to 0 for all Z such that X transpose GX, Z's transpose GZ, that's a G, greater than or equal to 0. Okay? So now if Z is satisfies this condition, right? This condition implies that also, right, if tau is greater than or equal to 0, then of course you multiply something which is positive times something which is also positive, then tau Z transpose GZ is also greater than or equal to 0. Right? So essentially, obviously, this is a sufficient condition, right, for positivity everywhere. So now let's say Z transpose F Z, right, the condition we have here. So let's suppose F is greater than or equal to tau G, right? That implies that if we multiply on the left and the right by Z, that Z transpose F Z is greater than or equal to tau Z transpose GZ. And of course, on this set, Z transpose GZ is greater than or equal to 0, and tau is greater than or equal to 0. And so we have that Z transpose FZ is greater than or equal to 0 on this set. Right? So in a way, right, this condition seems like it should be conservative because we're making F not just greater than or equal to 0, but greater than some tau times Z transpose GZ greater than or equal to 0. So this is making not just the term greater than 0, but greater than some other term, right, which is also positive on the set. Right? So it seems like we're relaxing the condition. This is a sufficient condition. But it turns out this is actually necessary, right? For any f such that f Z transpose Fz is greater than 0 on the set, there exists a tau such that this is true. So that Z transpose F of Z is greater than the tau times this quadratic form itself, right? So that's an interesting. So it's necessary if, and now I should, the necessity, right, is if this set itself that you're considering positivity on is not thin, basically, if it has an interior point, right? So basically that means, right, so if we consider the orthant, right, obviously that has lots of interior points. Basically, it's saying that your ellipsoid is not degenerate. It doesn't. So normally we're looking at ellipsoids like this. In the special case where it wouldn't have no interior points is when the ellipsoid's flat, looks like this, right? So there's an eigenvalue which is 0, right? Zero singular value in G. Okay. So anyway, this is a very important LMI, or a very important tool in our toolbox, which allows us to enforce LMI conditions on quadratic sets. So, and as we'll see, right, if we just inspect the condition over here, right, this should give us something like a necessary and sufficient condition for positivity, or for quadratic stability of this parametric uncertainty case. So I'm going to take a brief break here, and then come back and give those LMIs, having introduced the tool, in just a moment.